And welcome back. So we are still in chapter 5. We're now in section 6. We we glossed over section 5 for chapter 5. And we will come back to it at a later point in this semester. But I will hold off on commenting about that for right now. Let me kind of tell you what we need to accomplish with this video. So what we want to be able to do, right? The goal is to be able to take derivatives as well as to integrate various types of functions. We've had exposure to many different types of functions, and we've taken the derivatives of them. Other functions that are of extreme importance are inverse trigonometric functions. So to kind of guide the lecture, let me start with, let's start with just a couple quick facts, right? So we know that the period of the sine, we'll focus on, just sine, cosine, and tangent. We won't focus right now on the reciprocals. But the period of the sine function, cosine function is 2 pi, right? So in other words, we'll just look at sine for a second. So as we begin here at 0, and we continue, by the time that we get to 2 pi, we have one full length, right? One period of the sine curve. Now, from here, it's just going to repeat itself, right? We know that trigonometric functions are periodic. They're periodic, meaning they just continuously repeat themselves. Now, what we learned in the previous lecture, right, is that in order for a function to have an inverse, it has to pass the horizontal line test. So we can see right now that the sine function fails the horizontal line test. So if you ask me, does the sine function have an inverse? I have to say no. The sine function does not have an inverse, right? It's not 1-to-1. It fails the horizontal line test. So maybe the next question would be, well, wait a minute, Professor, if the sine function does not have an inverse, then why is there an inverse button on my calculator for sine? Well, that's a very good question. So how do we go about doing this? Well, and you can imagine that, if you don't mind a silly analogy, just imagine the sine curve as a piece of string. And what we're going to do is we're going to make 2 cuts. What's left is clearly not the original sine curve, right? It is it has been altered. But what's left, obviously depending on where you make your cuts, but in this particular case, we have decided to make a cut at negative pi over 2 and pi over 2. And you can clearly see that the reasoning is because it extends the full range of the sine curve, right? We know that the sine curve proceeds from -1 all the way to +1. So, but this is completely arbitrary, like many things are in mathematics. But we have decided to make a cut at negative pi over 2 and pi over 2. We throw the rest of the sine curve away. This new altered sine curve does pass the horizontal line test. It is 1-to-1, and therefore we can invert it. And that is what you're going to see right here. So you can I wish I was able to stack one on top of the other, but remember the symmetry, right? Let me see if I can draw that better. So we have this y equals x line. We have this y equals x line. And you can see how the altered sine curve and its inverse have symmetry about that line. You can also see, just highlighting from the previous video, look how the domain from negative pi over 2 to pi over 2, right? We made a cut at negative pi over 2 and pi over 2. The domain, after you invert it, becomes the range. The range becomes the domain. Now, we're not going to go into great detail of the domain, the range, etc. of all the various trigonometric functions. I have instead just plotted that information for you here. But what you should know, and if you don't have to believe me, you could test me. If you have a calculator readily available, whether you have degrees, radians, nevertheless, so if we're gonna move from sine to the inverse of sine. So if the domain is from -1 to 1, on your calculator you can try taking sine inverse of, say, 3. And your calculator should give you an error message, right? And that makes sense because 3 is not within the domain -1 to +1. So now eventually we're going to practice a little bit just to make sure we understand the inverse of these trig functions. And I'm in your pre-calculus course, whether you had me or if you had someone else, hopefully they would have, or I would have, went into great detail about inverse trig functions. I'm simply just giving a cursory glance of those ideas, and then we want to be able to do calculus with them. So you do want to have this information readily available, right? Because you want to be able to make sure your function meets the requirements of the domain and the range, etc., because before you start trying to take derivatives. So on the next page, what I've kind of posted here are just the parent functions of these inverse trig functions, right? So this is, we have the graph of arcsine, the graph of arccosine, arctan, etc., etc. And again, the arc, the reason why you see it written as arcsine here, arcsine of x, just to make sure there's no arcsine of x, is the same thing as using the sine inverse notation that we learned before. I prefer the arcsine, or like you would translate that as the angle whose sine is x. But really quickly, this is probably, if you are awake enough, this is really important. So let's start with what you know. Now you know that sine is a function, right? So if it's a function, you have to give it an input in order to get back out an output. And the input that we give sine is some angle, right? It could be in degrees, it could be in radians, but we have to give it an angle, and it gives us back out a ratio, right? The opposite over the hypotenuse. Now, obviously, since domain and range switch, notice that when we come down here to arcsine, now the input is opposite over hypotenuse, and the output is an angle. And I'll say that one more time. The input is the opposite over the hypotenuse, right? And if you're using the inverse sine button, what you are getting out, the output, is some angle, right? That's the point. You have the measurements, you want the angle. So we're using the arc the inverse trig buttons to do so. So really quickly, I'm not going to stay very long on example 1. So how would we translate arc sine of -1? My apologies, arc sine of -1/2. What do we do here? How do we evaluate arc sine of -1/2? Well, let's start with what you cannot do, right? You cannot grab a calculator, plug in our inverse sine of -1/2, hit enter, and then write some decimal. That's not quality work, right? We want the exact answer, not some approximation. So just to make sure, in case it's been a while, let's go ahead and translate this. So let's say arc sine of -1/2, it equals something. We don't know what that something is yet, right? We're going to call that something y. Now, to help us, right, because you want to be able to grab your unit circle and look up this answer. So let's go back to sine. So that would mean sine of something equals what? Well, remember, the domain and the range switch. So since inverse sines give you angles, we're gonna place our y here. So that means sine of some angle, we don't know what that is, sine of some angle is equal to -1/2. Well, now this is easy. Right now we grab our unit circle, we take a look at where, if you can imagine, we're kind of looking at where is sine equal to -1/2. And you just got to be careful, right? Because remember, sine is dealing with the y value. So you just got to be careful because there's going to be two points, right? There's going to be 2 points where sine is equal to -1/2. We have to choose the one that is within the domain and range, right? So where does sine of what angle equals -1/2? Well, that angle would be -pi/6. Again, if you're kind of operating without that unit circle in front of you, this can be somewhat frustrating to try to imagine. So probably what you should do is you should pause the video, go into that math notebook or go online, find a unit circle somewhere so that you can have that guy in front of you and follow along. And I guarantee you this will make sense once you take a look at that unit circle. Okay, so what else do we need to have? So do you recall in the previous video that let's just go back and use the same language, that if you have f of x and you have g of x, right? So here we have two different functions, and you recall in the previous video that if these are inverses of each other, right? If f of x undoes g of x, if g of x undoes f of x, then do you recall what happens when you take the composite of them? Well, hopefully you remember that the composite of inverse functions are going to cancel out all of the operations, and you're just going to be left with x. Now, why do I revisit that concept? Because I want to show you how a little trick that you can use that's that not a lot of students think about when they're solving equations. So for example, if you were trying to solve this equation for x, right, you have arctan of 2x minus 3. Now, what I will do, I'm just going to rewrite that using tan inverse, the way that it is on your calculator, the way that your previous professor may have written that problem. But the question still stands, right? If you want to solve this equation, to solve it, you want to be able to make a statement about x, right? X equals what? Well, how do you do that, right? How do you get x out of here? Well, remember, inverse functions can undo themselves, right? If I'm trying to be informal in my language, so that the concepts are clear, but sometimes being informal is not good either, because it can lead to some sloppy language. But nevertheless, let's see if this makes sense to you. So if I want to get x out of here, right, I want to solve for x, then tan inverse, if I were to take tan of tan inverse, that would be like if I took your age and multiplied by 2 and then divided by 2. Do you see how I would undo what it is that I originally did? So what I'm going to do is I'm actually going to take tan of both sides of this equation. And the point is, if I take tan of tan inverse, or tan inverse of tan, what you're going to see is these functions are going to just cancel each other. So let's go ahead and do that right now. So let me take tan of the left side of the equation, and I can do that as long as I'm willing to take tan of the right side of the equation. So let's start with the left side. So tan of tan inverse, that is going to undo each other. It's going to cancel out. What you would be left with is simply 2x minus 3. Now, tan of pi over 4, remember pi over 4 is 45 degrees. It should make sense to you. A 45-degree line cuts right through that line of y equals x, right? It's a 45-degree angle. So if x is 1 here, then y is 1 here. If x is 2 here, then y is 2 here. You can look that up, and tan of pi over 4 is just simply equal to 1. Now we have just a baby two-step algebra problem. Add 3 to both sides, and divide both sides by 2, and there you have it. So we've solved our equation. You can always plug it back in just to make sure, but all is good. Now, no calculus yet, but we're almost there. So how do we use some of those right triangle trigonometry techniques that we had developed in pre-calculus to answer the following questions, right? So it says given. So here's what we're given. We're given the fact that y is equal to sine inverse of x. Right? So that's the given. What do they want? Well, we want, just with that information alone, with this information alone, how do we find cosine of y? All right. So can you and I agree that if you're going to use the arc sine button, if you're going to use the sine inverse button, then what you're going to get back out is an angle, right? That's the point. So in this case, the angle is y, right? Arc sine is y, so therefore that's the y is the angle. So here is our angle. All right. Now we know that sine of theta is defined as the opposite over the hypotenuse, right? So in this particular case, what we have is a hypotenuse of 1. We have a unit circle. And what is the opposite? Well, in this case, notice what's left here. Remember, the input into arcsine, the input is the opposite over hypotenuse. So if I take the opposite of this triangle and divide it by the hypotenuse of this triangle, all I get is x. So that tells me that I am dealing with a hypotenuse of length 1, and of course the opposite side would have to equal x. Okay, well, at this stage, what do I know? Well, I know that my hypotenuse is equal to 1. I know that one of the legs of my right triangle is equal to x. If I have two sides of a right triangle, I can just use Pythagorean to figure out what the third side is. So in this particular case, the third side would just be the square root of 1 minus x squared. Okay. So where do we go from here? Like, so what are we trying to do? Well, we want to know, let me go ahead and now that we've built our right triangle, let's see if we can use this right triangle to figure out what cosine of y is, right? That's the goal. What is cosine of y? All right. Well, maybe we should start with the definition of cosine. All right, so my apologies. So cosine of some angle is simply defined as the adjacent divided by what? But divided by the hypotenuse. All right. So this is fairly straightforward, right? I mean, if all I do is if I just give you this right triangle and I ask you what is cosine of y, well, cosine of y is the adjacent. So if I'm here, what side is adjacent to me? Well, here. So adjacent divided by the hypotenuse. So the hypotenuse is 1. The adjacent is just the square root of 1 minus x squared. So division by 1. So what is cosine of y? Cosine of y is the square root of 1 minus x squared. And there you have it. All right, I'm just going to give you the answer to part B. The question was, given arcsecant of the square root of 5 over 2, can you find tan of y? Well, I'll go ahead and tell you that tan of y, you should be able to get 1/2. If you got the energy, if you got the time, pause the video, see if you can draw out that triangle and see if you can arrive at the result that tan of y is actually equal to 1/2. Finally, so let's get into some derivatives. And the good news is the derivatives are formulaic, right? It's in other words, if you have to imagine, right? You have to imagine, if you will, that forget about the derivative part. You have to imagine that this function is of some value to you. I don't know what it is that you're trying to model. I don't know what it is that you're trying to do, but this function is of some value to you, right? And you would like to be able to start calculating rates of change of that function. Well, in that case, the good news, the overall good news is that the formulas are fairly straightforward, and it's more or less once we've defined u, as long as we know which derivative formula we're using, we're for the most part just how to put it, we're just filling in, right? We're just using the formulas to find the derivatives. Let's just do one. So in this case, start with A. We would like to take the derivative of arc sine of 2x. Now I'm coming up here and I'm grabbing the derivative formula for arc sine, and it's simply u prime over the square root of 1 minus u squared. Okay. So in this case, whatever is inside of your arc sine would be what we're going to define to be u. So here u is defined to be 2x. Now looking at my formula, I'm going to need to have u prime, so let's go ahead and do that. So u prime, so derivative of u with respect to x is just 2. And I'm also going to need to have u squared. So let's go ahead and get that out of the way. So u to the power of 2 would just be 2x squared, or in other words, 4x squared. So I now have all the pieces, right? So let's just plug everything into the right spot. So this is going here. This is going here. And what is the derivative of arc sine of 2x? Well, it's just simply 2 over the square root of 1 minus 4x squared, right? So fairly easy. I mean, just fairly straightforward. Let's go ahead and the only thing that we're going to skip over b, because that one's fairly straightforward as well. I will write the answer for you. So the answer to b is 3 over 1 plus 9x squared. Let me go ahead and do, let's go ahead and do a little bit of a harder one. Let's go ahead and do c. All right, so we want to write, so we have arc sine of the square root of x. We would like to take the derivative of that. Okay, so let's go ahead and rewrite the square root of x, right? We know the square root of x is just x raised to the power of a half. Okay, this was an optional step. It's just sometimes that's easier to when we have to go through and take the derivative, right? So, okay, so let's start. What the game is, what are we going to define to be u? In this case, u is the square root of x, which we're going to rewrite as x to the power of 1/2. Again, since we're dealing with arc sine, it's just u prime over the square root of 1 minus u squared, so that's not bad. So if we now have u, let's go ahead and find u prime, and we also want to find u to the power of 2. All right, well, let's start with u prime. U prime is just 1/2 x now to the power of negative 1/2. Let's see if I can write that better. Okay, and then we'll go ahead and do u squared in just a second. So I'm kind of running out of room. Let me see if I can save myself a little bit of space like this. All right, so u prime is 1/2 x to the power of negative 1/2. That makes sense, just simple derivative, right? So, bring the 1/2 out front, minus out front, and then minus 1. So if you have 50 cents, you take away $1, you have negative 50 cents, right? Negative 1/2. So let's go ahead and we don't want to have these negative exponents. This is just going to be slightly confusing. So let's get back. That would be 1 over 2 x to the 1/2. We'll go ahead and write it as 1 over 2 square roots of x. Okay, so this is just a little bit of manipulation. So here's u prime. So u prime, I'm gonna get rid of d. So u prime over the square root of 1 minus u squared. All right, so let's go ahead and take u squared. Well, that's fairly easy, right? So if you take the square root of x and then square it, all you have is x. Let's go ahead and put everything in the right spot. So it might look like this. So let's start with u prime. So 1 over 2 square roots of x. Right, so this is going here. And that's got to be over the square root of 1 minus what? U squared, which is, in our case, just x. Okay, so you have the right answer. It's just sloppy, right? You have this complex fraction. You got a fraction divided by a fraction. You can clean this up. You can just rewrite this as 1 over, let's see if I can, 1 over 2 square roots of x times the square root of 1 minus x. And of course, if you have, let's just make sure you see, if you have the square root of 3 times the square root of 4, that's just the square root of 12. Likewise, if you have the square root of x times the square root of 1 minus x, you can think about that as 1 over 2 square roots of x minus x squared. Right? So you're taking this x and distributing it into that radical so that you only have one radical. Okay. Let's go ahead and take a break. And when we come back, we'll finish up this section. See you then.